I still
French
have
one.
it, man. I still have it. There is no back seats. Now it's just my truck.
There's no back seat?
No, in the Picasso, I still own Picasso.
Yeah.
And I use it just as a truck. I removed everything except my seat. And now I use it as a truck.
You are online now, Mattia?
On YouTube?
Okay. Yeah, on YouTube. Let's start the
Then you go for, yeah.
Okay. So, good afternoon all. The Federal Institute of Mato Grosso, Campus Primavera do Leste, have the pleasure to announce the beginning of the journey of education, research, and extension. It will happen in the days 20, 21, and 22 of October, okay? And the event will be 100% online, open to the participation of all the community. We have now the presentation of the engineer Mattia Lago. Yep. The presentation, it's about the biomedical application of additive manufacturing. Mattia Lago, it's engineer and a researcher. I worked with him in the Università degli Studi di Padova, the University of Padova. And we performed some researchers there about material science and those stuff. But I will let Mattia Lago introduce herself, okay? Mattia, you are welcome. Thank you very much for your disclosure.
Hi, everyone.
And feel free to start your presentation and to present yourself, okay? Thank you very much.
Yeah, thanks, Arturo. So, hi, everyone. I'm an old friend of Arturo. I think I met him in 2017, is it right? And back then, I was a researcher at the University of Padova. And I was working in duplex stainless steel, some special kind of stainless steel. And the year after, I started working on additive manufacturing, so complete different topic. It was on Institute of Nuclear Physics. I don't know if any one of you ever heard of it, but it plays a major role in the study, in the quest for nuclear fusion. And basically there is a big experiment in France that where they are trying to use to get energy from the fusion. And in 2019 and 2020, I was working with this Italian group, and mainly we had the task of producing some heat exchanger. And my boss back then bought this 3D printer, laser 3D printing for metal, to 3D print this heat exchanger, these heat sinks, rather than making them with traditional techniques. These machines were brand new back then, but we had to figure out how to use them. And also we had to pay them back because they were really expensive. So my boss back then tried to get some money back by doing some work for private companies. And me, I was in charge of doing some tests for the biomedical application. I know many of you, when you heard biomedical application, you think about prostheses and stuff like that. But me, I had to do some test parts for wheelchairs. And that's what I'm going to tell you in a while in my presentation. And just to finish, to present myself briefly, last year I quit with Academy because I got a nice opportunity of job with a private company. It's called Lago. It's an SPA. It's currently leader in master alloys of gold, basically a complete different field, you may think. But Lago is also producing powders for 3D printing, laser 3D printing, especially silver and gold powders. And I joined them. I was in charge of running this small unit. It's called Paumet. I was in charge of production of powders. But then they had this idea of open a new branch of the company, a branch dedicated to 3D printing. And I am now in charge of build this division from nothing, from scratch. And my bosses made a big investment of a new kind of 3D printer, not laser one, like the one I'm going to talk to you in a while, but binder jet prints. So now I'm managing facility preparation, dimensioning of the lines, cooling water for furnaces, and all this kind of stuff. So now I work in a complete different topics. Still, there will be a part of research because we will have to figure out how to use this equipment. So I'll return to be a researcher in a while when the facility prep will end. But for now, I'm doing, let's say, a different job. I'm managing the workshop, building of it, dimensioning, coordinating the contractors, and so on. But this is another story, and don't want to bother you with this. And I'll proceed with the presentation, the work I did it for biomedical application of additive manufacturing, as you can see in the first slide. It was in collaboration with a private company, as I already told you. It's called Progeria Team. It's kind of famous in production of wheelchair. And that's why the biomedical thing come from, because it was a project to build parts in additive for a wheelchair company. And this company is established near Venice, where I'm living. Let's say I'm living in Venice, but I'm not. I'm 60 kilometers from it, in Padova. And the company is very close to Venice, and they are making really lightweight wheelchair, tailor-made. They made unique products, custom-made for Paralympic athletes or just people that are not so lucky, let's say, that they cannot walk on their own. They make really nice products. You can go check their website. Anyway, the printer I was using, they were made by US, which was the pioneer of 3D printing. May think is a new technology, but I think they start working on it in the late 80s. So it's almost 30 years old technology, but it started to be widespread only 10 years ago, let's say. Anyway, we had two machines. They are still there. My former colleagues are using them. We had a small one and a big one. And I don't know if you know how 3D printing is working. You can see a small animation. Basically, you have a part here. It's a tower from the chess game. Basically, you have your STL model that you draw that you draw on a CAD. I was using a CAD from Siemens back then, and then you slice, okay, in the Z-axis, layer by layer. I was using a slicing of 40 micron or something, and then a laser, a real high powerful laser, melt the powder that are homogeneously spread by a coater. The laser melt the powder only where it's needed, where your object is going to grow, and layer by layer, you spread a new fresh layer of powder. The laser will melt it selectively where it's needed. Then a recoater blade will plane it flat, again a new layer of powder, and so on until you complete the job. That is producing a part like that. It takes a long time, but the process is completely automated. Let's say you can grow an item 10 millimeter per hour. So it's quite slow, but you can get a nice precision. Tolerance was 0.1 millimeter. I think now they got better. You can understand that if you want a tight fit, for example, you want to fit a bearing, an 8.7 kind of tolerance, you cannot achieve with this machine. Later on, you have to do some machining with lathe, CNC, a mill, but you can get a almost net shape thing, net shape part. And it's just imagine if you want to make that pieces from a bar, you have to do it on the lathe, you have to machine a lot. Or if it's a bigger item, you have to do die casting before. So if you want to make not so many objects, 3D printing is really a deal breaker, especially if you're working with odd material, exotic material, refractory metals that are not easy metals to process, okay? And speaking about how big the items you can print, dimensions are not so big, okay? The bigger of the two machines, the one you can see in the upper right corner, the platform is 250 by 250. In the base, and the Z-axis, we have 300 millimeter, but still you can make a huge amount of things, okay? You cannot build big parts of equipment. You cannot make the head, the cover of an engine, okay, of a combustion engine. But you can make a lot of complex things without going through dyes and complex stuff. So that's just a brief introduction of what additive is. Presentation is not meant to explain this in details, or we stay for hours. I can speak for hours about how it's working, what you can do, what you cannot do. Of course, there are limitations, but ideally, it's a deal breaker. And you can print really odd things that even thinking to make it via milling, it would take ages. Or maybe it would be impossible. Anyway, this, as I told you, you can process a lot of materials. Depends on the powder you are loading in the machine. Wheelchairs, as you can imagine, they must be light. And the parts I had to print, they were to be printed out of aluminum, an aluminum alloy. Because later on they were welded in a frame. It turns out that the most common kind of aluminum alloy is this one. Maybe you know for its application in foundry, because there is silicon that fluidify aluminum. Anyway, it's the most common one, okay? We bought this powder from a European company. Main characterize of a powder is the particle size distribution. It's a Gaussian shape. I mean, you cannot buy powder, all the powder to be 50 micron. There is a range. Since the layer of printing was 50 micron, because we wanted to be quick in production, average dimension of the powder was almost 50 micron, as you can see. And the items you can get from it, you can machine them quite easily. You can weld them. You can also coat them and polish them. It's not easy to polish aluminum because it's a soft alloy. Anyway, you can polish it. So the private company said, okay, this material may work for us. Give it a try. And why don't you try to make these pieces? Because we had a Paralympic athlete that is going to have an important Paralympic contest. And why don't you try to make his wheelchair more lighter? So the first item, the first part that I print for them is this part, okay? You can see it from the zoom. Basically, it's a bracket. There are two hexagonal screws that tie it to the tubular frame, and on the other extremity there is the pivoting of the front wheel. And they send me an STL file, and they say, we want the same external geometries, but make it more lightweight. And if these things will work out, we'll see if we can shift to producing it via additive without going through dies and a lot of machining, because this was die casted. So the original part is what you see on the left. It's you can guess it's not easy to make it. It was, as I already told you, die casted, and where the front wheel is accommodated, it was milled to the right tolerance, as well that oval shape where it is clamped via the hexagonal screws to the tubular frame. So first idea, let's say quite brainless idea, was let's make it let's make it more light by alloying it. So remove the inside. Is what you see on the right. Basically, first idea is I take out the inner parts. I will make it like a pipe, basically. You can do it quite easily on a CAD. Probably you work with CAD, with 3D CAD. It's a quite easy operation to do. So I leave it 2 millimeter, but see, removing a lot of material, of course, will make the component more weak. I ran some simulation with ANSYS, quite common software, and it turns out, as you can see, that if you remove material, you get some weak points. I will not go through the detail of the numerical things behind it, but it was not the optimal ways to go. Obviously, the weight, you lower it down a lot. Yet, as you can see, it will deform a lot. You will go from a 0.05 millimeter of deformation on the maximum loaded point, the red one, to 4 times bigger, and start to be quite a lot, okay? And this was in static deformation. So imagine in a dynamic thing, because the wheelchair will be used, it's not going to be statically loaded. I mean, yeah, it's going to be statically loaded by the way the person that is sitting on it. But this was for a para-athlete guy. So, and he was the kind of guy that is jumping from stuff. It's basically skateboarding, but did it on a wheelchair. So you can imagine a lot of stress. And so it didn't sound safely to me, nor to the company and to the guy, of course. So there must be another way, and it was using honeycomb. Now think of doing it in a traditional way. Hollowing is still a tremendous thing to do, but try to do this. So instead of having a bulk section, you just have a 2 millimeter skin, and inside you fulfill it with a honeycomb structure. That is a super stiff thing, okay? Just to think about doors, the doors of your house, they are not hollow inside. You have 2 layers of plywood, and inside there's an honeycomb made out of cardboard that Cardboard itself is nothing. But when it's trapped between two layers, the door you get is much lighter and still it's really stiff. So that was the way to go. The simulation said it was feasible. The machine can handle it without any kind of problem. And we printed this kind of parts, and it proved to be working. It was as stiff as the original, but 30% lighter, which may sound not so much, but with professional sport guys, it means a lot, okay? Only drawback was it takes an eternity to print, 10 years of lead time, okay? I was printing 4 of them, by the way, but it takes 10 hours to print all 4 of them. But the machine was running on its own, just during the night. So it takes 0 effort. When you load the CAD file with the CAM file as well, the machine runs on its own once you load powder. It's a really easy task to do. And it proves that was the right way, and they were quite happy with it. So then they asked me for another part. Still is a part of the wheelchair that is holding in place the front wheel. But this time is this part, okay? This highlighted. And believe it or not, prior to this, they were making it with hydroforming. Hydroforming, basically you have a die, 2 half dies, okay? You put a pipe, a standard tube of aluminum, and this die is hermetically closed, and you pump water at super high pressure, and the pipe will deform, and it will follow the shape of the die, and you get that really complex shape you see in the picture that is later on welded. And they say making the die is super expensive. It's not easy to engineer the die. It's not easy to process the die. The die will deteriorate over time. Plus, in the wheelchair, okay, let's go back. You have 2 of them, and they are not the same pieces because they are chiral, like hands, okay? You have a right piece and a left piece, okay? So you have 2 dies. You need to have 2 dies, so you double the cost. Now you can get, if you produce tons of wheelchairs, the same model, okay, after a top number, the dies will pay for themselves. But you need to hydroform tons of that pieces, okay? If you are running a small production, it really is not worth it, okay? You will spend 50k euros in dies to sell a wheelchair that costs 2k. So if you have to make just 1 wheelchair, it's a crazy thing. It's against any business idea, okay? It's simply madness. So I say, try to print it. Again, we want to have the same geometry. They were not risky guys, because with additive manufacturing, you can print things in a way that you will never make with traditional technique, because you have to use the capabilities that additive gives you. These guys were not so brave to risk it. They want to say, I just want to evaluate the capability of this technology. We don't know. So they told me, print it exactly the same. I want to see if it's still working fine, if I can weld it, and if you can produce a piece that maybe is lighter. Okay, so you see the original part. Not easy to make. It's not a symmetric part. The section is really complex, and also is not constant. Okay, in the axis, okay, if you imagine an internal axis, the section is not constant along that axis. And see also, of course, you make it via hydroforming. You still have to do that odd cut that is going to match the frame where it's going to be TIG welded. So still it was a two-step process: hydroforming, okay, and then mill it to that not easy shape at the ends to match the frame where it's supposed to be welded. So again, I make the wall thickness less thick. This time you still see an honeycomb inside. It was not to make it more stiff because the geometry is still quite robust, okay? Main problem of additive is that people will sell the machine, they will tell you, you can print whatever you want. That's a lie. If you have some odd angles that are overhangs, the parts will collapse during printing and you will have to put some supports. That is something you will understand while printing. No one will ever tell you when they sell you the machine, okay? Because people that are selling are really good at what they do. They are commercials. Maybe they know nothing about technical, but they are really good at selling. So when you print the part like this, you have to put a lot of supports. Otherwise, the part will collapse on its own, okay? And the structure inside is a kind of a support itself. It was meant to support the inside, okay? But say, since the supports are not stiff, because you will break with a ply, okay? You will torque them, you will break them at the end. They are not strongly welded to the part, otherwise it's going to be a mess removing them. So I say, instead of having supports inside that are giving not stiffness, not strength at all, let's put the honeycomb inside that is going to be much stiff, and no one is going to see the inside of this pipe because it's going to be welded anyway. And so that's what I did it. And of course, the TIG welder had to be much more skilled because the wall thickness was reduced to 1 millimeter than the 3 millimeter of the initial thing. Also, printing was not so easy. I had to make several try and error things to figure out all the supports. And you see also some blue things. Those are cones that they extract heat from the part, because the part, basically you are welding powder with a powerful laser. You have fusion and instant solidification. So there is a lot of heat that has to be removed. If you don't do that, the part will somehow bend, okay? It's basically like you're welding pipes. You're welding a frame thing. When you're welding a frame thing, okay, made out of tubular steel, if you just weld if you start welding, you make a long, okay, pass just on one side, the thing will hopefully bend and you will have a crooked frame because all the heat is just one side and you will have thermal stress. Working with 3D printing, basically you are welding powders and it's the same. You have to take into consideration this thing. This is basically all experience. At the end, at the beginning I was thinking, it's a printer, I just have my CAD file, I'll do the slicing layer by layer. I will put aside the machine, start, I go home, and the next morning at work, I would see my part done. It was not the case. I failed many, much more than I want to admit. And this was really a pain in the butt. But at the end, with a lot of supports and these cones that act as heat sinks, I managed to get a perfectly flat part because those guys, they had some measure probes, and they were getting they were doing retro engineering on the parts I was printing. So they were getting all the quotes from the actual parts I was making for them. And the guy that was running this machine was very skilled, and it was never, it did not forgive any of the mistake I did it. But anyway, somehow I managed to produce many of them. We ran a batch, and actually one of these was in the wheelchair of the guy on this Paralympic athlete. By the way, he didn't win, but that's how it's life. Anyway, again, when you 3D print a part, when you finish, you remove all the powder that has not been welded, okay? Welded by the laser, and you get your print, your part that is basically welded on the platform. You can see on the upper left corner, that is a part that is on a wire cutter machine, because you have to cut these pieces from a platform because they are actually welded. Or if they are supported, as you can see on the picture in the center, you see the part, the bracket I showed you in the first case study. You see there is the part in a strange orientation, again, to avoid some odd angles, to avoid overhangs at least, diminishing the number of overhangs to have the least amount of supports possible. Still, I put a lot, as you can see, it was really cumbersome. If the part is supported, then you may be able to break with apply. Still, if you have access to a wire cutter machine, it's much better. You'll also struggle much less. Anyway, after you remove all the supports, okay, you have the pieces, as you can see in the two main pictures. What do you have to do prior? First time, I just cut with a wire cutter or with a band saw if wire cutter was not available. If the parts were just supported with some light structure, I was using apply. What I was getting was bananas, basically. Okay, bananas. Parts that were supposed to be flat, they were bowed. So I cursed a lot, and remember what I was telling you before. Basically, we're actually welding powder. And there are a lot of thermal stresses. The parts is welded on a platform that is really stiff and thick. When you're cutting, all the tension are released, and you get these bananas. So we figured out, there's plenty of tons of these in literature. Anyway, I did a try of skipping this heat treatment to make the parts as less expensive as possible. But it turns out the heat treatment was mandatory, and just a stress relieving, okay? So it has to be done prior to support removal. Since I was also I am a material engineer, some metallographic tests were carried. The company was mainly interested in mechanical tests, okay? Because they were really skeptical, and me, I was the same, that parts like this can behave like traditional made pieces. And first of all, here we can see a section, okay, of the part. Of course, I did not cut the fancy pieces. I did some small cubes, and I did metallographic test on it, since you have to destroy the piece, basically. So on the Z section, which is along the grow axis, okay, along the Z axis, you see a really, how can I say, fish scale thing, okay? Basically, each scale is one layer of powder that is being melted. So you see the scale under micron. You see basically the layer thickness was 50 micron or so, which was the average dimension of the diameter of the powder. In the other, you can see how the grain look like. Okay. And since the cooling rate, the heating rate and the cooling rate are super fast, grain structure is really fine. So it means high mechanical resistance. If you compare this value here, I had to do it. I forgot to put the value of a standard piece of aluminum. But if you don't believe me, go check it on your own. But the yield stress of an aluminum part of the 4000 series, which is one of the most shitty kind of aluminum you can get, you will see yield stress 20% lower, maybe 30% lower, okay? Compared to the as-built. As-built has not been stress relieved. The heat treated is stress relieved, and of course the grain will grow a bit. So the microstructure will be less fine. So the yield stress will decrease a bit. Still, the yield stress is much higher, but than traditionally made piece. If you check this value, you see why you measured in both axes. That is quite normal. Normal properties of additive pieces is that they are anisotrope. When we think about metals, we think about isotrope properties. Let's take apart sheets. Okay, it's not the case because along the lamination axis the properties are higher. But let's think of a milled part or a piece that is being turned on the lathe. There is no difference in mechanical properties on the axis of rotation or the orthogonal axis. Additive pieces has this drawback that in one axis they are more tough, and as you can see on the z-axis they are less tough, because usually on the z-axis you will have porosities due to gas evaporation during the welds of layer by layer. It's true that this machine work in argon or nitrogen atmosphere, because if you try shoot a laser, high powerful laser, 400 watt is a lot, on powder in oxygen in atmosphere, you will get a fire that is something unbelievable. We see firecrackers basically, because powder is so much reactive. Also, you have to be really careful handling metallic powder. In Lago, where I'm producing it, we are working in a white room, okay? Everything is ATEX. No sparks at all, and we are all dressed with anti-static things. The floor is anti-static to avoid sparks, so powder handling is not so easy. Additive for sure, field, additive technology does not come cheap. Machines are not cheap. Facility preparation is not cheap also. But the parts you can get, it's a deal breaker again. Is that the initial investment is not meant for everyone. Additive company, there will be few with a lot of technology inside. They will be innovation center of excellence. It's not like lathes or milling machine. It's small shop as a milling machine. It's small shop as a lathe, even a CNC now. Additive is still an elite kind of things, not meant for everyone. Mainly in Europe, there are services. In Italy, there are, I think, 5 or 6. At least I'm speaking for the customer I have in Lago. I have 4 or 5 customers, and in Germany, probably there are 15 of them. We are selling also to a company in Estonia, that are making jewelry out of silver, but there are not so many. Still, it's developing thing. They are making huge steps. Each year, the number of companies that are working with powder and printing is increasing, but still, it's a small thing compared to milling and machinery shops. Just to give you an example. On the last line, I'm also speaking about relative density. Relative density because since there are some voids due to gas evaporation, gas that is trapped in the powder, maybe powder got a little bit of humidity, so there is some water evaporation. The density is never 100%. And this, of course, will reflect a bit in fatigue resistance. So the good 3D printer guys are the guys that are able to get the geometry they wanted. Okay, of course, precise fitting has to be milled or turned anyway, but they are also good on parameter of the printer. Okay, laser parameter, laser scan speed, power of the laser, layer thickness, and they are able to get a relative density as closer to 100% as possible. So you have pieces that can also be used if fatigue is a concern. You may know that aluminum is still a quite easy metal to process. And turns out that with the machine, they also sell us a couple of titanium grade 5 alloy. And this company I was working for, this Progeria team, they were making also some kinds of wheelchair made out of titanium. And so I made the same pieces also out of titanium. Layer thickness was a little bit less, 40 micron, because titanium is quite a refractory metal, not easy to melt. Pro of titanium, of course, the ratio of Young modulus or metal of strength ratio of these two properties divided by density is much higher than steel and much higher than aluminum because of the intrinsic property of the metal. So basically, you can get a geometry that is lighter but stiff at the same moment. What is the main con of titanium? It's the low thermal conductivity. And you say, why? It's for a wheelchair. Why do I have to care? Well, if you 3D print it, is a big of a deal. Because remember the thermal stresses I was telling you about? If with aluminum, you have to take them in consideration somehow. With titanium, the thing is critical. Thing was so critical that sometimes the job was failing. Basically, the thermal stresses were so high that the support things that prevents the part to collapse while printing because of overhangs, angles above 45 degrees that you have in complex design like these parts, they were ripped off from the platform. Just imagine the amount of thermal stresses that you have during the process because you are melting instantly powder. Sadly, one part I was not able to make it, the tubular thing. Dobbs top half, you can see the honeycomb inside. And also heat treatment is after, providing that you can print it. Of course, you can print everything of titanium. They do incredible job. They make bone plants out of titanium. They make pieces of bones out of titanium. they use the intrinsic properties of additive pieces to be rough, okay? You see the picture, it's not a machine part. It's not shiny, okay? But for bones, it's a big pro, because a part that is rough, your body will stick better to it, okay? So sometimes it's good to having rough pieces, okay? It is a tough topic anyway. Anyway, heat treatment is much tougher. You need a good furnace. Not the one I was using here. You see the rainbow. That can be nice to see, but metallurgically speaking, it's a mess. Basically, some oxygen was inside the chamber of the furnace, and it gets inside, and oxygen and nitrogen of the air can really make titanium brittle. It was glass. Basically, it was glass. On the holes, okay, you see the holes. That holes is where the head of the screw is accommodated. On the other part, okay, in the other half, there is the threading. With this heat treatment, I did perform 650 degree 3 hours of stress relieving, plus oxygen and nitrogen from the atmosphere. The pieces were so brittle that the support, okay, when I was breaking them after wire cutting, I broke them with a ply. They were not broken as you expected a metal to break, bending and bending and bending. Like you're cutting, you have to cut a steel wire. You don't have a ply, a cutter. You bend. Okay, it's fatigue. Those pieces were flying around like sharpness. Okay, it was really scary. And when I tried to tap, okay, the M6 thread, the tap inside it broke, because that thing is like glass. It's martensitic. It's impossible to work. Also, when we machined the bearing fit, the tools lasted only one job. So definitely there was something wrong on the treatment. I repeated much higher temperature, and the martensite was did transform in alpha plus beta structure, which is a structure that you can easily work and is not brittle. You cannot have a brittle part in a wheelchair for a sport guy. Anyway, you may wonder, 3D printing, you tell me you can print everything. Why you are tapping the threads of the M6 screw? Yeah, as I told you, you can print basically everything, but the tolerance is 0.1 millimeter. And for an M6 thread, you get the point. Better go with a tap. But you can get the 5 millimeter hole that is to be tapped from. You are mechanical guys, so you know better than me that for an M6 screw, you need a 5 millimeter holes that is later tapped with a proper tool. We call it maschio in Italian. I don't know how it sounds in Portuguese. Anyway, yeah, you can print the hole, 5 millimeter hole, but it's better to be tapped by hand. Still, for precise fitting, tools are still the way to go. And I think tools will be the way to go for still many years. That is the mag structure with a wrong heat treatment. And you see it's the two pictures on the left. You see a lot of small needles, okay? This is martensite, that make the parts so tough and brittle. And with the proper heat treatment at much higher temperature, of course, the hardness is much lower, but that's not the point. We don't want a hard piece. We want a tough piece. And that is alpha plus beta phase. Basically, is the transformation of martensite. That is the good structure you want to have on a titanium piece. So, to finish, since it's almost 15 minutes, I'm speaking non-stop. It's true. Additive brings a lot of benefits. Now, of course, I am working with it. It brings bread to my table, So it was back then. It's now the company I'm working for, so I cannot speak bad about it. It's true. It brings a lot of innovation. First, you can also think in a different way to design your part. It's called topological optimization of components. Basically, if in a part you don't need the mass, the weight in a zone, in a place of this part, if it's not needed, you can remove it. I will make you an example from the architectonical things. Since I am Italian, the stereotypes that we are descendant of the Romans, okay? Probably you have seen some pictures in books, or if you've been to Rome, we see a lot of things, arch structure, okay? And there are holes, okay? Holes. And say, why they are putting holes in a wall? Well, there are some, make nice things, like nice holes, okay, for windows. So, because in that part, for example, Romans discovered that there was no need to put bricks, because in arch, all the load is carried on the outer, okay, due to the geometry of the part. You see the CD line they were making, aquedotto, okay? You see, it's made out of arch. No need of having bricks or rocks in the center part. They discovered that things are still holding nice after 2,000 years. Also in small things like mechanical small parts, it's true. You discovered via simulation or via experience. Experience is always better than simulation. If you can do a real test, it's much better. Anyway, cost. So simulation, somehow your bosses will be happier with it in your future. You say, mass is not needed here. With additive, you can not have mass weight what is not needed. Not easy to do with milling and lathe and lathe, or achievable, but you have to work a lot. You have to produce tons of chips. What else? You can do structures, parts that are super difficult to get with traditional tools. A big example is fresh graduated mechanical engineers go working in companies that produce parts. They make a nice design. They think it's perfect. Oh, my boss will be so happy. Or we get a promotion, blah, 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 blah. And then the foreman of the workshop, you see the drawings, the map, say, okay, but who is going to machine this piece on this inside board? Is it going to be a mole doing it? A mole is a talpa, that kind of animal that is digging galleries in the ground. Usually some drawings, some maps that freshly graduated engineers show to experienced machine guy. The machine guy will say, engineer, but how can I do this? How can I do this internal geometry? Well, with additive, if you have an additive machine, you can do what you want. Speaking about odd and interior cavities, let's say. Still, you have the problem of tight fittings, tight tolerances. So milling machine operator and lathe machine will never be dismantled, okay? Lathe machine guy, milling machine guy, CNC operator, there will be work for them till the humanity will live. Another revolution that is more from a business point of view. It's a problem of warehouses. Warehouses are huge. Warehouses are really, really huge. And because they have to accommodate tons of pieces, different pieces, because customer want spare parts. Part is broken. I want one. I want it now. In our world, competitors are are like wolves. Okay, warehouse must have everything. They take huge footprints. Okay, if you have a 3D printing machine, you have a database of STL part of CAD file. A customer call you, I want this spare part. You don't have to have it physically in your workshop. In one day, you will have it printed. Let's say you have also two machines, some zones, some areas. Still, in a couple of days, it will be ready to deliver, and it's still a really acceptable lead time. Just imagine if you don't have that part in the warehouse and you have to make a new one. Maybe it's part of an old equipment, of an old car. The dies are, who knows, maybe they've been thrown away by the main manufacturer. So you have to machine from a bike piece. Just imagine the revolution in terms of warehouse management. And also, as I explained in the case I described before, if you're producing a small series, small batches, you don't need molds. You don't need that hydroform die. You don't need it. You just print. And, or for example, that wheelchair, the parts I printed for that wheelchair, it was for an athlete. But maybe another athlete is more tall, or he weighs more, or the anatomy of the wheelchair does not fit this guy. You want the wheelchair to be taller, to be less tall, to be more wide. If you have the mold for hydroforming, for example, you can produce only that geometry, only that. You want it 1 centimeter longer? No way. You have to make another mold. And if the mold is expensive, basically your business is blooming, let's say. Or you have to find another supplier if you cannot make it on your own. So think about this, and you will get why additive manufacturing companies are growing. I'm speaking about European market, but I know each year the tons of powder I am producing in Lago, it's growing. It's growing because every year new companies are buying this kind of machine. Mechanical workshop or workshop that work for hospitals to make prostheses. Okay, your leg is different from the leg of another person. Don't speak about your own leg. Your young guys, legs of your granny. Maybe your granny needs a new bone. Okay, it's not some part that you make. Okay, in series. Each granny has different legs. It's obvious. Okay. Additive in this case is the way to go. Or for tooth printing. Okay, tooth are another kind that, especially in Spain, they have a big market of tooth, 3D printed tooth out of chrome cobalt alloy. That with the proper treatment, they will become a kind of ceramic alloy, ceramization of metal. It's a tough topic. Anyway, I hope I did not bored you. That was me a couple of years ago. Now I got 30. I hope you don't see the difference. Those were my colleagues back then. Anyway, it's my mail. That's my private. If you have some things to ask us in the future. And that's it. If there are some questions, Arturo, what you say?
Okay, Mattia, thank you very much for your presentation. It was very good. I really appreciate that. And let's go to the questions, right? That's okay for you?
Yeah. Just read them to me and.
Okay. So let's start. Let me check the questions here. Okay, the first question is From Bruna Lorenzon. She's a student of the electromechanics course.
Bruna, you are from Veneto. Bruna
Lorenzon, it's an Italian name.
From Padova.
Lorenzon, it's from Padova.
Yeah.
Okay, she's asking if you made with aluminum and titanium, right?
Yeah.
You can use also other materials?
Yeah, stainless 316 is typical material you use for try and error. It's real cheap.
Oh, okay.
Yeah.
You can use any kind of metal, right?
I'll tell you the materials that are the one I saw or the one I work with. 316, that aluminum, Al-C10Mg, titanium, grade 5. There is a precipitation hardening steel, 17.4 pH. That is the American name. What else? Chromium cobalt for teeth. There are a lot of special kind of steel, Kodak steel, Maraging steels powder. Copper is a quite tough metal to print.
Because I think it's too soft. I don't know if.
No, main problem of copper.
The fusion point, maybe.
No,
the melting point.
No. Main problem with copper. My first month in Lago, I was working in a small project for trying to print copper with a medium-sized laser. Is that laser on machine are infrared, okay?
It reflects.
And copper is red. So you have the laser is not absorbed by the material. You just got it back to the lens. And you are destroying the lens, basically.
Yeah. Okay.
Brass is not so easy because there is zinc, and zinc is evaporating, okay? But bronze is really easy to print. Classic bronze, 90% copper, 10% tin. What else? They are doing some try and error with duplex. That guy, the one next to me, the smallest guy in the group, now he's working in another powder making company based in Venice. It's called Pometon. And they are working on a biphasic steel that is advanced at high strength steel. And the company is working for, just bought a big gas atomizer. And that guy is in charge of R&D. Back then, it was my colleague at the Nuclear Physics Institute. You, Arturo, you know him for sure. Anyway, pretty much tungsten. You can 3D print tungsten.
Wow.
Tungsten is a pain in the butt to work with in traditional way. They are making tools out of tungsten. So imagine turning tungsten with a tungsten made tool.
Yeah.
You can print carbides.
Oh.
You can make your own tools. So there is a lot of research, both universities and private companies. They are trying to figure out the best parameters to print each different kind of materials, and powder making companies there is a lot of competition because there are not so many companies that have atomizer in-house. So there is a lot of competition, a lot of research, and it's a really growing business.
Okay.
Yeah.
Thanks for answering. We have more questions here. The Professor Williams Ribeiro Mendes, he's an electrical engineer. He's a professor, my colleague. He's asking, there's some study to replace the titanium in these applications. And he's also asking, what's the best material for this kind of impression and manufacturing? These two questions.
I don't get exactly.
Okay, the first point is there are some research or studies to replace the titanium in these applications that you.
In body parts.
Yeah.
Okay. To say the truth, I would answer a kind of a bullshit. I'm not an expert in body things. I know for spinal things, they are using tantalum.
They still using titanium.
Tantalum.
Tantalum.
Yeah, for spinal plants. But really don't ask me why. I think biocompatibility is higher than titanium. I think that is the reason. And one of the guys in this picture, the one that looks like Chester Bennington from Linkin Park, the guy in the middle, is working with tantalum. And he managed to print some parts. Also, tantalum part is currently produced only in a Canadian company, French-Canadian company. I remember he was getting really hot cracked pieces, so it's not easy to work with, but for at least for spinal implants, it seems the way to go. But is combo research, material scientists, and doctors. So doctors said tantalum is the way. Now you guys, you engineers, find out how to deal with it. But I cannot tell you in details why tantalum is better. So I would say some not precise things. I just know that tantalum seems to be the new way to go.
Okay. The other question is which is the best material for this kind of process for the 3D printing? Which is the material more easy to work, I guess?
I would say me personally, aluminum, it was a good benchmark. Mostly, I would not say it's cheap. But powder metals are definitely not cheap. I would say now let's don't speak about this recent crisis in supply of metals, but let's speak prior to COVID. In Italy, I was buying stainless €3 per kilo, okay? In powder form, a spherical one, so gas atomized. 1 kilo of stainless is €30, so 10 times more, okay?
No.
So it does not come cheap, definitely. And with aluminum, aluminum was not easy to process. Research spent a lot of times back in the early 2000s. Now it's super easy to work with because aluminum was reflecting a lot. The way to go is making the powder more matte, so it will reflect less the laser.
Okay.
Yeah. Basically, you add some impurities in the composition, and you lower the laser reflectivity at the specific wavelength of the laser, which is red in this case.
Okay. Also from Williams, we have some more questions. When you produce or when you make a part of, let me check the question, just a moment. Okay, when you made a part from some machine or something else, you make a study of strength distribution in the parts or no?
We did some tests in field.
Yeah.
Now this presentation was about pieces of wheelchair, but we produced parts for many other applications. In Veneto region, in all Italy, there is a big thing for the fashion industry. Lago, my company working with, for example, produce alloys for wedding rings, for necklace, for all that kind of things, jewelry, and Italy is famous for these and also for fashion things, shoes especially. We were making high heels for shoes for girls with tough shape. We did a study for Yves Saint Laurent. Their logo was the heel of a shoes, not the traditional inline one, but there was some twisted in the leathers, and that was tested fatigue, okay, because we did some pieces for a factory that is producing heels. We did some fatigue test. Okay, there is a standard for shoes. I didn't know back then, but I saw it with my own eyes. Basically, a heel, a shoes with a heel. There is a machine that simulates the number of steps a girl will take with that shoes, and a shoes with an AM titanium heel was mounted in this benchmark, and it withstand, and it didn't broke from fatigue. Okay, so then we did also some electrodes, spot welders. Maybe you know it, guys. The evolution of traditional spot welders. Okay, it's welders. It's not spot by spot, but you have two circular electrodes that are counter-rotating, and you have two sheet metals, okay, and you run it through these two electrodes, and you have a long weld line, okay. They are water-cooled also. Mm-hmm. And basically there is a company that is making channels for climatization. Okay. Think about big commercial center, for example. And this electrode lasts longer than a standard made one. Not because the material is better, okay, but since it was additively made, the exchange area inside was much bigger because we made an intricate shape of channels, and so the exchange area from the fluid and the electrode was higher, and so the higher the lifespan of the tool. That's the example I can tell you. But my parts, this guy did this race, and that's it. I don't know how the wheelchair is now. If he throw it away, if he still use it, I don't know. But we had one tool that survived more than a traditionally made weld tool, and is scientifically a thing test for the high heel shoes. So somehow we tested, but not as a material engineer, as an in opera way. So okay. I hope this is enough.
Okay. One more question from Williams. He's asking if there's some study that did a comparison between the machining process and the 3D printing process, and which one is more efficient, and if the quality of the part justify the energy spent in the process.
Yeah. That is a big thing. We can speak about it for hours. But I already told you, you want to fit a bearing. Let's say you want to make a shaft, okay? Don't make it additive. Turn it from a stock. Shaft is not a complex piece, okay? Even if it's a camshaft, don't do it this way. But if it's a shell of something, okay, a complex piece that you usually die cast, you have to make one or two. Additive is the way to go. In a part like that, you don't need high surface finish. You don't need high tolerances. Maybe you have a gasket in this shell. Okay, machine, get a tool, just a light finish pass where the gasket is going to be fitted. You need a perfectly flat side, okay, for the gasket, plus the groove. Okay, just a light pass on the milling machine, it's fine. Just imagine produce that part from a solid stock. So additive is not replacing the traditional ways. It helps the traditional way. Okay, it's like when you're producing lathes, for example, the Norton box where the gearbox is. Okay, no one is milling it from a cast iron piece. A foundry company found in pour liquid cast iron in a sand die, okay, and then you machine it with milling only what is needed on mating surfaces. Just think about additive as a in-house small foundry shop where you can get a piece in 10 hours, one day, with zero struggling. You just load powder. Basically, you pour powder inside the machine. You just level the bed of powder. A trained guy, like I was back then, that I was using it every day, in 20 minutes, me alone, I was able to load 100 kilos of powder and leveling the platform. And then press start. If the CAD preparation was done the proper way, the machine was running itself effortlessly. While if you are machining things, I'm speaking about manual tools I'm more experienced with. For example, lathe, you have to center the piece. Then you have to shift it inside the jaws. So you have to recenter it again. It's true. Maybe you are a trained machine guy. You do it in a matter of nothing, but still takes time. So, yeah, to say the truth, to load and unload an additive manufacturing machine, you don't need a trained guy. You don't need a super high skilled worker. Just pouring powder and leveling a plate. Nothing fancy on it, nothing difficult on it. So the two things, traditional machinery and additive, they will live together. It's not that they will disappear. It's like, for example, stone. The first material that men learned to use back in the Neolithic era, I don't know. It's not that now stone disappeared because there is concrete. The concrete, you pour it and you get the shape you want. You still build things made out of stone. Stone did not disappear. It's nice to look. It's more fancy than a concrete slab. It's the same for additive. It will not replace machining. They will live together, like every other form of technology man discovered so far and to the days to come, basically.
Okay. We have another question from a student. Elder Frota, it's also a student of electromechanics course. He's asking if the 3D printing it's a very long process. How long? It means in time, because he's complaining about that the impression that we made here is very, very long.
Yeah. Yeah, it's terribly time consuming. It's true. Of course, you can make it faster. You can play with the parameter. That's true. You will lose things in terms of precision that you may want or may not. Anyway, yeah, terribly long compared to other kind of processes. But it's effortless. It runs on its own during the night. No need to supervise the process if everything is being properly made, because sometimes some jobs, print job, may fail. Like with titanium experience I had that I explained you previously. But providing everything is being perfectly setted, machine run on its own, effortless. This new kind of machine, binder jetting machine, that we are buying in Lago, they are 10 times faster, even more than this laser machine. You have other kind of problems because it's a two-step process. You have a sintering in the middle where binder will evaporate and the powder will, in a solid state kind of process, they will merge together. So you have a shrinkage that is not what is happening in laser. In laser, you don't have any kind of shrinkage, while in binder jet process you have. But is much faster, and like Volkswagen is using this binder jet printer right now with SLM. Companies were a little skeptical. Why? Because of the huge lead time that in fact this guy, sorry, I cannot remember the name, has correctly pointed out. It's terribly long, it's true. But just imagine producing a super complex part. If you're making cubes, it's not worth it. Just set up a mill and make some passes, and it's going to also be more fun. You will see some sparks, some chips flying around. But try to produce one part like the one I showed you. We can go back in the presentation. Try to make one of these completely with a milling machine. You will die in the workshop. You will have to work Sunday, Saturday, or during the night. Make tons of setups. Even if you are a CNC skilled guy, you really that's a hell of a challenge, with an AM machine. Really, you have to be not even a good cut guy, like an average cut guy, like I am. I'm not a super pro cut guy. I think I'm just average, but I managed to do that. So, yeah.
How long did it take to print this piece on this part?
The big clamp bracket with the screw. Some years has passed. If I remember it right, 10 hours.
10 hours.
But I printed 4 parts. So if you 4 hours and 10 hours, I got 4 parts.
4 parts, okay.
And 2 was
so 2.5 for each part.
And 2 was left, because there is one right part and one left part.
Okay. Now I have one question. Can you just move the slide again, please?
Così?
No, where there's the honeycomb.
It's basically everywhere.
Yeah.
Yeah.
Okay. For all kind of parts, the best structure is the honeycomb. It's very common. Also, we have a professor here that are doing a research with drones, and he made some parts with a honeycomb also inside. And I was checking that everybody uses this structure, and for sure. What's the reason, and this is the best one, and why?
You want the cool answer or the real answer?
You can say both.
I will tell you the cool answer.
Okay.
Because physically, it's a structure that the load with that the load will follow the shape of these things. You have a lot of surface to dissipate the load.
Yeah.
The real answer, the CAD preparation file, the slicing software, which is Magic from Materialize Belgium, it costs tons of money. Okay.
Oh.
And in the basic package, there is just the honeycomb. Okay.
Okay.
And it is auto-generated by the software. It's not me with the CAD drawing this. The software automatically goes from the bike one, to that one in a matter of 2 buttons. Okay.
Mm-hmm.
So, as I was telling, there is no need of super skilled guys. Not super skilled CAD guy, not super skilled manual guys. So.
Okay. Thanks for the answer.
Yeah.
And one more question about the supports that you used in the 3D printing. You made it also in the printer, or no?
Sorry, about
the support.
The supports.
Yeah.
The supports is generated by the CAD prep software. This Materialize Magic. It's a hell of a software. It costs a huge amount of money. In this software, you can let the software decide. Each year it gets better. Okay. Mm-hmm. Still, you have to check it, especially for tough parts. And you choose the best orientation where you have the less amount of overhangs. So you have the least amount of supports, because when you break the supports with apply, the surface will be not so even, It's like breaking a weld. You will have a lot of dents in the surface. So you can trust the software. The software usually gives you something to be on the safe side. Okay? You will be sure to bring home the job.
Mm-hmm.
But you will have tons of fun with the ply. There are much clever, smart ways to limit the amount of supports and of polishing after. Because if you have a support, you have more surface finish to do later on. But yeah, the software gives you a big hand.
Okay.
In nesting, especially also in nesting, because you have a lot of flexibility in additive. You can print this kind of a horn, okay? It reminds me of a horn, okay? And you can also print rings or odd things, all in the same batch. As long as you can fit things in the platform, the machine does not care about the complexity of the thing. The laser go on its own. It will follow a G-code generated not by you, okay? Because generate the G-code for this, something to go crazy. It will follow something that the slice software will do. Probably some of you guys work with plastic, 3D printing of PLA. It's really easy to print a PLA part. Now they are selling this 3D printer for plastic like toys. 200 euro, maybe less, you get one. It does its own job. Honestly, for 200 euro, you don't get the top-notch thing, okay? You don't get the HP machine. But you still get your pieces done. If you have a plastic 3D printing, you will see how easy it is. Also there you have support, by the way. With metal, it's a little bit more cumbersome, but it's not so much more difficult.
Okay. I think that is the last question. Is there any corrosion study about the 3D printing and other processes to compare,
Yeah, it has been done. Not by me. In Padova, they did it. And they are on the same level. 3D printing part and the standard part, they are acting the same. Why? It's true that you have some porosity. A decently made 3D printed part, you can reach 99.8, 99.9%. So the number of void is really small, but most of the voids are inside the part, not in contact with the aggressive solution or environment. So no pitting at the end of the day, especially if you polish really well the surface.
Okay. I think there is no more questions. Someone else in the YouTube wants to ask something. Let me check here. One moment. Okay, no more questions. Mattia,
okay.
Thank you very much for your presentation, for the answers.
Thank you so much.
You are welcome here. You are also a very big friend, very good friend, a very close friend of mine.
Yeah.
Okay.
Yeah, me too. Yeah.
So feel free to contact me and contact us when you want. Okay.
When these COVID things will be over, I will come for sure.
Okay.
I'm waiting for you, or bring some of your students there. Here in Italy, it's going to be a pleasure.
Okay, thank you. If you have the opportunity, for sure we will go. Thank you very much. So that's it. Thank you all for watching the presentation. Thank you again, Mattia.
Thank you to everyone. Okay. I hope I did not bother any of you.
No, for sure
any of you, sorry. It's been, I think it took the double of time we thought it was going to last.
But it was a very good conversation.
Yeah, thank you. Thank you.
Very good contribution also for the Institute, because I guess that you are the first foreigner that do a presentation here for us. So we are very happy, very glad with that.
Yeah, I'm proud about it.
Okay.
Thank you.
Okay. Thank you. Thank you all. So we can close the room. Bye-bye.
Yeah.
Ciao, ciao.
Thank you. Thank you. Ciao, ciao. Ciao.